Hello friends, welcome to this lecture on computer-aided power system analysis. We have been discussing the basic procedure of weighted least square estimation method. We have already discussed that what are the basic techniques of this, and we have also looked into the calculation method. So, today in this lecture we will now start looking at one simple example to illustrate the calculation procedure with a numerical example. So, what we have is let us say that we do have an circuit, and this is the circuit. So, everything here is basically 1 ohm, and we have got two voltage sources V1 and V2, and we have put 4 meters. There are 2 ammeters Z1 and Z2 and Z1 and Z2. So, I mean this is our actually first measurement, this is our second measurement, and there are also 2 voltmeters, this is Z3, this is Z4. So, essentially what we are trying to measure is that we are simply trying to measure the current flow through this path, current flow in this branch, voltage across this branch, or essentially the voltage at this point, because I mean this point is taken as the reference point, this particular point is taken as a reference point, and we are also measuring the voltage at this node with respect to measurement. And these meter readings are Z1 is 9.01 ampere, Z2 is 3.02 ampere, Z3 is 6.98 volt, and Z4 is 5.01 volt. Now, you see that all these values are not exactly an integer values, because as an example here probably the actual value is 9 ampere, but then here because of this meter errors this value is being actually read as 9.01 ampere. Similarly, probably the true value of this current is actually 3 ampere, but here because of this meter error it is being registered as 3.02 ampere. Similarly, probably the actual or rather the true value of the voltage at this node is 7 volt, but again because of the error it is being read as 6.98 volt, and then similarly probably the actual value or rather the true value of the voltage at this node is 5 volt, but again because of the meter error it is being registered as 5 volt. So, now we have also discussed in the last class that we do take the weights as the inverse of the variance. So, then therefore, so then essentially accordingly these two ammeters are essentially found to be more accurate. So, then therefore, their weights are taken to be 100, this is also 100, this is also 100, and then these two meters are not that accurate. So, they are a little more inaccurate. So, then therefore, their weights are taken as 50. Now, our unknown state vectors are or rather essentially our unknown quantities which we try to estimate from these 4 measurements is V1 and V2. So, then therefore, the first thing we have to do is to express these measurements with respect to the or rather we have to express these measurements in terms of this unknown voltages, or rather in terms of the unknown quantities. So, here what we do is, so as we said that we do express the unknown quantities. So, then we do have our measurement model is we have seen is essentially that we have seen that our measurement model is Z is equal to H x plus E. So, now here to start our state estimation algorithm we have to know what is this matrix H. Now, this matrix H can be computed from the circuit analysis of the given circuit. So, let us again draw it now, I mean how it is done. So, then essentially what we have to do, we have to essentially express all these measured values in terms of these two unknown voltages V1 and V2, which can be done only by through appropriate circuit analysis. So, now I mean let us do that. So, our circuit is something like this. And then I think it is so our circuit is like this. So, this is V1, this is V2 and this is R1, R2, R3, R4, R5 and here we are measuring I1. So, this is my Z1, we are measuring I2, so this is my Z2 and we are measuring here V2, R2 and we are also measuring here VR4, V across R4. So, in our measurement model Z1 is equal to I1, Z2 is equal to I2. Please note that here we are talking about a DC circuit. So, then therefore, there is nothing called this absolute magnitude or angle. So, this is all everything would be just numerical values. Z3 is VR2, that is the voltage across this resistance R2 and Z4 is VR4. So, that is what is our measurement. So, then essentially we have to find out that what would be the expressions of I1, I2. Now, let us say this point I say VA, let us say this point is B. So, let us say this particular voltage is VB. So, then therefore, we say that VA, VB, we have to now find out this matrix is essentially H11, H12, H21, H22, H31, H32, H41, H42 into V1, V2. So, we have to now express I1 in terms of V1 and V2. So, we have to now essentially find out these coefficients H11, H22 and all these 8 coefficients from the circuit analysis. And here of course, we note that VA is equal to VR2 and VB is equal to VR4, that we note. So, now to do this, how to do this? So, now we have to do our standard circuit analysis. So, at this point and at this point we apply this nodal equations. So, if I do apply this nodal equations, what I get is that VA minus V1 by R1 plus VA by R2 plus VA minus VB by R3 is equal to 0. I am just applying KCL at this point. Now, here if you note that all these resistances R1, R2, R3, R4 and R5 are equal to 1 ohm. So, then therefore, because all resistances are 1 ohm. So, then therefore, we can write down that VA minus V1 plus VA plus VA minus VB is equal to 0. So, this equation turns out to be 3 VA minus VB is equal to V1. So, this is equation 1. This we are doing as R1 is equal to R2 is equal to R3 is equal to R4 is equal to R5 is equal to 1 ohm. So, this is our first equation. Now, we apply KCL at this second point. So, applying KCL. So, this I write that here applying KCL at node A, we get this. Now, we applying again, now applying KCL at node B, what we get is, if we look at this, VB minus V2 by R5, so we get VB minus V2 bar R5 plus VB by R4 plus VB minus VA by R3 is equal to 0. So, then therefore, VB minus V2 plus VB plus VB minus VA is equal to 0, or in other words 3 VB minus VA is equal to V2. So, this is equation 2. So, I have got equation 2 is this, and equation is 3 VA minus VB is equal to V1, that was equation 1 from this. So, what we do is, from equation 2 I get 9 VB minus 3 VA is equal to 3 V2. So, let us say this is equation 3. So, 3 plus 1 I am doing, that is 9 VB minus 3 VA plus 3 VA minus VB is equal to 3 V2 plus V1. So, then therefore, this got cut. So, then 8 VB is equal to 3 V2 plus V1 by 8. So, then therefore, this is sorry, there is little mistake. So, then therefore, so I can simply VB is equal to this. So, that I can say that it is 0.125 V1 plus 3 by 8 would be 0.375 V2. So, this is the first equation. So, this is equation 4. Now, because I have got this VB, so now we have to now calculate VA. So, from equation 1, so 3 VA is equal to VB plus V1. So, VB is 3 V2 plus V1 by 8 plus V1, that means 9 V1 plus 3 V2 by 8, or in other words VA is equal to 3 V1 plus V2 by 8. So, then therefore, what I have got, VA is equal to 3 V1 plus V2. So, 3 V1 plus V2 by 8. So, it is 0.375 V1 plus 0.125 V2. So, this is equation 5. So, we have got these two voltages V and VB, we have got these two voltages V and VB. So, now after that we have to calculate what is I1. So, I1 is nothing but Now I1 is nothing but V1 minus VA by R1. So, this is V1 minus VA. So, this is V1 minus VA is 3 V1 plus V2 by 8. So, it is 5 V1 minus V2 by 8. So, it would be 0.625 V1 minus 0.125 V2. So, this is equation 6. And similarly, I2 is V2 minus VB, and V2 is, and VB is, what is VB? VB is 3 V2 plus V1 by 8. So, 3 V2 plus V1 by 8. So, it is 5 V2 minus V1 by 8. So, it is minus 0.125 V1 plus 0.625 V2. So, we have got all the expressions of this measurement values. So, now our equations are, so then therefore, equations are, now let us look at that what was our equation. So, our I1, I2, VA, VB. So, I1, I2, VA, VB. So, then therefore, so then in matrix form, so we have got I1, I2, VA, VB. There will be something, we will fill up this blanks, and this would be V1, V2. And so, now first thing I1 is 0.625. So, this is 0.625 V1 minus 0.125 V2 minus 0.125 V2. I2 is minus 0.125 V1, I2 is minus 0.125 V1 and plus 0.625 V2. So, plus 0.625. VA is 0.375 V1, 0.375 V1 plus 0.125 plus 0.125, and VB is 0.125 and 0.375. So, it is 0.125, 0.375. So, this is the measurement model. So, these are all measured quantities and this is the unknown x vector. So, then therefore, this is the H matrix. So, then therefore, we can simply say that my H matrix is given by, so this is my H matrix and this H matrix is given by 0.625 minus 0.125 minus 0.125, 0.625, 0.375, 0.125, 0.125, 0.375. So, this is my H matrix. So, then therefore, we can see that this H matrix is always evaluated on the basis of the circuit analysis. So, then therefore, H matrix is nothing but the relation between the true value of the measured quantities and the true values of the unknown quantities, and that can only be obtained by the circuit analysis of the system. So, this is my H matrix. So, now with this H matrix, we will now do our calculation. So, this is our H matrix. So, our H matrix is, we have already seen, 0.625 minus 0.125 minus 0.125, 0.625, 0.375, 0.125, 0.375, 0.125 and 0.125, 0.375 and 0.125, 0.375. And our W matrix is nothing but our W matrix is, and our W matrix, that is the weight matrix, is nothing but, we already said that it is a diagonal matrix. So, it is a 4 cross 4 matrix. So, it is 100, 100, 50 and 50, and these off diagonal quantities are 0, this off diagonal quantities are 0. So, then this is my W matrix. So, 100, 100, 50, 50. So, then therefore, we have got this H matrix. So, then we do H transpose into W, H transpose. So, this is the H transpose into W. So, we get this. So, H transpose W is given by this. After we do this H transpose W, then we calculate this G matrix as, this is the gain matrix. G matrix is nothing but the gain matrix. So, it is H transpose W into H. So, this is H transpose W, we have already got H 62.5 and minus. So, this quantity is H transpose W. So, this is H transpose W and into H. So, then it is this. So, it is a 2 cross 2 matrix. Now, we have already argued and we have already shown theoretically that if there are, if there are n number of values which are to be estimated, if there are n number of values which are to be estimated, so then in that case the dimension of the gain matrix would be always n cross n, irrespective of the number of the measurement used. Now, in this case, in this particular circuit, n is equal to 2 because our unknown quantities are V1 and V2. So, then therefore, n is equal to 2, and because n is equal to 2, so then therefore, our G matrix would be a 2 cross 2 matrix. So, then it is a this 2 cross 2 matrix. One thing we need to understand that it is a symmetric matrix. Now, how do I prove that this G matrix is a symmetric matrix? We will show it, but then we can show it very easily that G is equal to H transpose into W into H, and if I do take its transpose, we will ultimately get back this. So, then therefore, G is a symmetric matrix, and it is indeed a symmetric matrix, we can see here. So, G is a symmetric matrix. So, then now our estimated values x 1 hat and x 2 hat. We have said that always we do always denote our estimated values with a hat symbol. So, it would be G inverse H transpose into W into Z. So, then this is the G inverse. So, this is G, that inverse. H transpose W we have already calculated. So, this is H transpose W and this Z. So, this G inverse is this, then it is H transpose W, and Z is a vector. It is basically nothing but the measurement vector, and that is nothing but Z1, Z2, Z3, Z4. So, this into this, now this is a 2 cross 2 matrix and this is a 2 cross 4 matrix. So, then therefore, this whole quantity would be 2 cross 4 matrix. So, then I have got a 2 cross 4 matrix. So, this into this is nothing but a 2 cross 4 matrix, and this 2 cross 4 matrix I got. So, this into this, and then we substitute the values of Z1, Z2, Z3, Z4. So, we please recall that our values are 9.01, 3.02, 6.98 and 5.01. So, then if I do this, I get this estimated values. So, these are the estimated values. Now, from this estimated values we can possibly infer that, well, probably the true values of this V1 and V2 would be somewhere probably this, I mean V1 would be 16 and V2 would be 8, but well, now let us look at that what is the estimated measured value, or rather what is the true value of the measurement. So, now what happens, that if this is the estimated value of the x, so then therefore, I can also estimate. Now, we are taking that as if that this estimated values are, we are assuming as if that the estimated values of x are the true values of x. So, then therefore, if I substitute these true values of x into the expression z is equal to h x, so then I get the estimated values of z. So, now this is the H matrix and this is the estimated values of x. So, then h into x hat. So, this is giving me this particular, this is the z hat matrix. So, this is the estimated value. So, then therefore, estimated errors are the values obtained by the meters, the actual values obtained by the meters, that is 9.01, 3.02, 6.98 and 5.01 minus the estimated values of the measurements. So, this is this. So, we can see that these estimated errors are pretty small. So, we can possibly think, yes, our estimation is reasonably correct. Now, here the point is that here this calculation only has been done for a particular set of measurement. Now, please note that if in this circuit, even if we take these measurements repeatedly, that is, if I take this set of measurement right now and then if we take another set of measurement by utilizing the same meters and the same circuit after let us say 10 minutes, we may get simply some other values of the measurement values. Now, suppose for example, we take another set of measurement and then for Z4, that is that VB we get 4.4 instead of 5.01. Suppose let us say this is 4.4 instead of 5.01. Let us say something happens to this meter. So, it is now giving me a reading of 4.4. Now, until unless I do have some other means to know that whether this meter has gone out of order or not. So, then therefore, we have to accept these values 4.4 as the actual, I mean we have to accept these values as the correct value given by this meter. So, if we use 4.4 and if we again do this same analysis, you see, so then I get this value. So, if you can see that earlier my estimated values were 16 and almost is equal to 16.00 and 8.0, but now my values are 15.86 and 7.75. So, these are now considerably changed. And also if I now do this estimated, now if I now compute estimated errors are now much more increased. Now, from these two sets of measured values, our question is that which one should I accept? Is there any method for us to accept that, well, this is the true one, or let us say the this particular set of values is true one? How do I decide upon this? As such, just by looking at these measurement values, we do not have any idea that which one should be more correct. So, then therefore, we have to do some kind of statistical analysis on these obtained values, some kind of statistical analysis on these obtained values, and then based on those statistical analysis, we have to decide that out of let us say these two, which one should be the acceptable. In fact, here we have taken only two sets of measurement, but please note that when we are doing this exercise of state estimation, this particular exercise of state estimation is actually a kind of continuous process. That is, we do take the set of measurements after let us say 5 minutes or after let us say 10 minutes or whatever it is. So, we keep on taking the set of measurements at a regular interval, and then at that same interval we also keep on estimating the states of the system. So, that means we are simply trying to monitor that what is happening to the system. So, then therefore, until and unless we do develop some statistical method and do apply that statistical method on a particular on any particular set of estimated values, we would be unable to decide whether these estimated values are really useful or not. So, then therefore, these questions are very important questions in the scope of this state estimation analysis, and we will start addressing these issues from the next lecture. Thank you.